Hello everyone, welcome back. In this video we are going to do occurrence and extraction of metals. This is a part of chapter 3 metals and non-metals, and from this chapter we have already done physical and chemical properties of metals and how metals and non-metals react. So I have shared the links in the description. You can check out those videos and then you can see this video also. Now let's get started. So let's start with the occurrence of metals. So metals occur on Earth's crust and also in seawater. In seawater they occur in the form of some soluble salts like sodium chloride and magnesium chloride, etc. So the main two sources we can say of metals, they are Earth's crust and seawater. So we have seen so many metals like gold, silver, platinum. So now we know the sources also. The next term is minerals. The elements or compounds which occur naturally in the Earth's crust. So these are the natural elements or compounds. Like gold, we have already discussed gold, silver. So all those elements or compounds. Ores. So at some places, minerals, they contain a very high percentage of a particular metal, and that metal can be profitably extracted from it. Like we can take the example of Kolar gold fields. Here gold mines were there. Very profitably gold was extracted, but now it's not there, but still we can take that example. You can see metal or ores, they occur in this form. Gangue, this is one term. So these are the impurities in the ores, like impurities in the form of soil and sand. And these impurities, they must be removed prior to the extraction of the metal. So before extracting the metal, gangue, it should be removed. So different processes based on the physical and chemical properties of gangue and the ore. So it is removed. You can see here also. See this gold, it's there, but along with the gold you can see sand and some impurities are there. So these impurities are gangue which has to be removed prior to extraction of the pure metal. Now how metals are extracted? We have already done reactivity series. So this is reactivity series starting from potassium till gold, it's mentioned, and with the help of reactivity series we'll understand how metals can be extracted from its ore. You can see here 3 categories are made. The first one is from potassium to aluminium, then zinc to copper, then gold and silver. So few like hydrogen, mercury, all those metals also, or all those elements also, they come in the third category. So here, see in the third one, these metals, they are very less reactive. They are unreactive, we can say. We have already discussed while doing the reactivity series that these below hydrogen elements, they are very less reactive. So then this is the middle one, like zinc, iron, lead and copper. These are moderately reactive elements, and then these potassium, sodium, calcium, magnesium and aluminium, these are highly reactive elements or highly reactive metals. So based on this, we'll understand how metal can be extracted. See these metals which are at bottom, they are non-reactive or less reactive or least reactive, we can say. Sometimes they occur in, or most of the time we can say they occur in their free states. But sometimes they occur in the form of their sulfides also, but most of the time they occur in their free state. But these elements, like in the first category and the middle one, which are highly reactive metals and which are moderately reactive metals. So these do not occur in the free state, but they occur in the form of their sulfides and carbonates. So then their sulfides and carbonates, they are converted into their oxides. Then from its oxide metal can be extracted. We'll understand how. So with the help of this flow chart, first of all we'll understand it more. Metals of high reactivity metals of medium reactivity and metals of low reactivity. These are the three categories of metals we have already discussed in reactivity series also. So metals of high reactivity, their metal is extracted with the help of electrolysis of a molten ore, and then pure metal is extracted. And metals of medium reactivity, medium we have already discussed, they are available in the form of their carbonate or their sulfides. So carbonates and sulfides, they are converted into oxide of a metal through these processes, calcination and roasting. So then this oxide further it is reduced to metal, then afterwards metal is purified. This is about the metals of medium reactivity, or the metals which are moderately reactive, not very high reactive. So these are the metals of low reactivity. If their sulfide ores are there, mostly they are available in their free state, but if they are in the sulfide or in the form of their sulfide, then roasting is done. So this is done directly by heating. So we'll understand it while doing the chemical reactions and chemical equations of them. Now we'll see how metals of low reactivity series, how metals or low reactive metals, they are extracted. So we have already done that silver, gold, copper, all these metals are less reactive or least reactive. So metals in the activity series, they are unreactive, we can say. Their oxides, they can be reduced to metals by heating alone. Now we'll take the example of cinnabar. This is mercuric sulfide. This is an ore of mercury. See, mercury is available in the form of its sulfide. So first of all, it has to be heated in air, then it will be converted into its oxide, then further its oxide it will be reduced to mercury. So this we'll understand with the help of chemical reaction. So this is sulfide of mercury, cinnabar, which is in solid state, and it will be reduced to mercuric oxide by heating. So that's what we have read now. On heating, the metals of low reactivity series, they can be reduced to its metal. So on reacting or heating the sulfide of mercury, it will be converted into its oxide. So from here, the end products are, or the products are, the oxide of mercury plus sulfur dioxide. See, because it is a sulfide, so we will get sulfur dioxide also. So we can balance this equation also. 2, so 2. And because oxygen, now we have 4 plus 2, 6. So here we can write 3 into 2, 6. So 6 atoms of oxygen this side, 2 atoms of mercury here, 2 atoms of mercury this side also, and sulfur, 2 atoms of sulfur this side, and 2 atoms of sulfur this side also. So this chemical equation is balanced, and you can see we have just heated mercuric sulfide, which is cinnabar, which is known as cinnabar, its name, common name. So this cinnabar on heating, it is converted into its oxide. Now this oxide, it is further reduced to the metal. It will be further reduced to mercury on heating. So we will get mercury, since it is oxide. So after, since we are doing reduction, and in first chapter also we have already done reduction, means removal of oxygen. See, so here we are just doing reduction, from its oxide we are getting the metal. Now let's write, because we have to write the states also. So this is solid state, oxygen here it is in gaseous state, this we got in solid state, and sulfur we got in gaseous state. This is in solid state, and mercury, this is in liquid state, because in its physical properties also we have done, mercury is the only metal which is liquid at room temperature. So we got mercury in liquid form, and this is in gaseous form. Again we can balance the equation. So 2. Now you can see 2 atoms of mercury this side, 2 atoms of mercury this side, 2 atoms of oxygen and 2 atoms of oxygen. We can see from the sulfide of mercury, just on heating we got the metal. So we have extracted the mercury from mercuric sulfide. Now let's do the next reaction. Now similarly, copper, which is found as copper sulfide in nature, can be obtained from its ore. We have just now seen the chemical reactions of mercuric sulfide or cinnabar. Now let's see the reaction of copper sulfide. So this reaction, it is very similar to the previous reaction. Copper also comes in the metals which are very less reactive. So copper sulfide of copper also, it can be directly converted or reduced to its metal by just heating it. So same thing we have to do like the previous reaction of mercury we have done. So we just have to heat it. First reaction, we will get copper oxide plus sulfur dioxide. So same reaction. From copper sulfide we are heating in the presence of oxygen and we are getting oxide of copper. Now this oxide, it will be reduced to copper on further heating. So the only difference is this: here we have to take copper oxide plus copper sulfide. So both of these we have to heat them and they will be reduced to copper. So here along with copper we will get sulfur dioxide, because we have sulfur here, so we will get sulfur dioxide. Now let's balance the chemical equation and write the states also, because every time whenever you are writing any chemical equation you have to balance the chemical equation and write the states also. So this copper sulfide, it is in solid state, oxygen in gaseous state, copper oxide, this is in gaseous state, this is in solid state, and this is in gaseous state. So both of these are in solid state, so S we can write. Copper is in solid state and sulfur dioxide is in gaseous state. So we can balance the equations now. So 2 sulfur, here we can write 2 atoms of sulfur, 2 here. Copper, now it is 2 into 2, it is 4. So we can write 2 over here. 2 into 2, 4. So 4 atoms of copper on both sides, 2 atoms of sulfur on both sides. Now we can balance the atoms of oxygen. This side it is 2 plus 4, because 2 into 2 is 4. So 2 plus 4 is 6. So again 3 into 2 is 6. So now this is balanced chemical equation. Now here we can see again we have to balance it. Copper, it is 2 plus 2, 4. Here it is 1. Oxygen again 1, but here that side we have 2. So here we can write 2, because oxygen we have to balance. So now oxygen 2 on both sides, but copper it is 1. 2 into 2 is 4. 4 plus 2, 6. So directly here we can write 6, because sulfur it's already balanced, 1 over here, 1 over here. So this is balanced chemical reaction and balanced chemical equation, and we have observed like in the case of mercuric sulfide, we have just heated sulfide of copper and reduced it into its metal. So now we have seen how metals of low reactivity they are extracted. Now let's move towards extracting metals in middle of the activity series, or which are not so reactive we can say, or which are not very less reactive also, they are moderately reactive. So the metals in the middle of the activity series are iron, zinc, lead, copper. So they are moderately reactive. We have already discussed this thing. So they are usually present in their sulfides or carbonates in nature. This thing also we have already discussed. So mostly these sulfides and carbonates, these are converted to their oxides. The reason is that it's easy to extract metal from its oxide rather than from its sulfides or carbonates. So that's why we have discussed 2 processes also, roasting and calcination. See, if any ore is in the form of sulfide, So sulfide ore, it is converted into its oxide by heating strongly in the presence of excess air. So this process is roasting. So basically you have to remember, when sulfide ore is converted into its oxide, that process is known as roasting. Now calcination. So we have discussed it can be available in the form of sulfide or carbonate. So when the metal ore is in the form of carbonate, so it is again changed into its oxide by heating strongly in limited air, and this process is known as calcination. So let's see reactions of both roasting and calcination. We have already done the definition of roasting, so let's convert the definition into this chemical equation. So we have zinc sulfide, we have to convert it into zinc oxide. So zinc sulfide, which is in solid state, we have to heat it in the presence of excess of oxygen. So oxygen is also in gaseous state, so we have to heat it. After heating zinc sulfide, it will be converted into zinc oxide, which is again in solid state, and the other product will be sulfur dioxide. Now we can balance the chemical equation. So here, this side 3 atoms of oxygen, so let's write 2 over here, because oxygen 2 atoms this side. So now this side we have 4 atoms of oxygen. So let's write 2 over here, but here now zinc also 2. So we have to write 2 here also. But here if we write 2, sulfur, it is also becoming 2. So that's why here also we have to write 2. Now oxygen, we can see 2 into 2, 4. 4 plus 2, because this also 4 plus 2 is 6. So here we can again make a change, because we have to make the atoms of oxygen also same. So 3 into 2 is 6. Now we can see this chemical equation is balanced, and we can see sulfide of zinc is converted into its oxide by heating it in excess of air, and this process is known as roasting. So in calcination, we have to convert metal carbonate into its oxide. So we are taking zinc carbonate. This we have to heat in limited supply of air. So that's why additional oxygen we are not taking, as like we have taken in case of roasting. Here only metal carbonate, we have to heat it and we will get metal oxide. Since it's a carbonate, so we will get carbon dioxide here. So we can write the states also. This is in solid state. This will also be a solid state, and carbon dioxide is in a gaseous state. We can check the equation also. Zinc 1 atom on both sides, carbon 1 atom on both sides, and oxygen 3 this side, 2 plus 1 3 this side. So this equation is already balanced. So you have seen in calcination, we are just heating the metal carbonate and converting it into its oxide. Now we have learned, or we have seen the reactions of calcination and roasting. We have seen how sulfide and carbonate is converted into metal oxide, or metal carbonate, or metal oxide. See, now the metal oxides, they are reduced to the corresponding metals by using suitable reducing agents like carbon. Like we'll take the example of zinc. Now we have got zinc oxide. It will be heated with carbon, and then it will be reduced to metallic zinc. So this also will see how the reaction is taking place. Now we have already got zinc oxide. See, in roasting and calcination, in roasting we have converted sulfide of zinc into its oxide, and in calcination we have converted carbonate of zinc into its oxide. So in both the reactions we have got its oxide. Now this oxide or metal oxide, it will be heated with reducing agent. So reducing agent we are going to use is carbon. So carbon is a reducing agent which we are going to use here. So we will heat this oxide of a metal with carbon, and it will be reduced to zinc. So here we will get carbon monoxide as the other product. So this reaction, again we have to balance the chemical equation and we have to write the state. So zinc oxide, it is in solid state, carbon is also in solid state, zinc is also in solid state, and carbon monoxide is in gaseous states, and we have to balance the chemical equation also. So zinc it's 1 on both sides. Oxygen, again it is 1 atom of oxygen on both sides. Carbon, again 1 atom of carbon on both the sides. So you have seen, after getting metal oxide, we just have to heat it along with the reducing agent. So carbon, we have used a reducing agent, then this metal is reduced to its, then this metal oxide is reduced to its metal. And reduction, again in the first chapter also we have done, reduction is the removal of oxygen. You can see here, oxygen is removed from zinc oxide and we are getting zinc. So sometimes, like the reaction we have done, we have used carbon as a reducing agent and we have got the metal from its oxide. But sometimes displacement reactions are also done. So these displacement reactions, they are done, metals which are used in displacement reactions are sodium, aluminium and calcium. Because in reactivity series we have done that these metals are highly reactive. So these metals, they will displace the least reactive metal or the metal which is less reactive from these metals from their oxide, and they themselves, they will get oxidized, leaving behind the metal. So we will do one chemical reaction so you can understand it in a better way. We have oxide of manganese. This we are reacting with aluminium. So aluminium, it will displace manganese from its oxide and it will form aluminium oxide, leaving behind manganese. So this is how displacement reaction is taking place. But in this reaction, heat will also be evolved. And this reaction is highly exothermic reaction, that the metal which we are getting, we will get this in liquid state or molten state. This manganese oxide, it is in solid state. Aluminium, it is in solid state. This metal we will get in liquid state and this is in solid state. Now we can balance the chemical equation. See, I have already made one video on balancing of chemical equation. If you don't know how to balance the chemical equation, you can check out that video also. I have shared the link in the description. So let's do another example so that you will understand it more. So we'll take oxide of iron now plus aluminium. So same thing will happen. Aluminium, it will displace iron from its oxide and it itself will form aluminium oxide. So iron will be left behind. Again it will be in liquid state, because these type of reactions are highly exothermic and due to this heat produced, the metal will be in molten state. So aluminium oxide we can write plus heat. Now you can see in both of these reactions, one thing you can observe, that iron, it is getting reduced. Reduced means, in chapter number 1 we have done, reduced means removal of oxygen. You can see from here, removal of oxygen is taking place, and here addition of oxygen is taking place. So we can say this is oxidation reaction. This is oxidation, here it is taking place, and here reduction is taking place. So that reaction in which both oxidation and reduction is taking place is also known as, or is known as, redox reaction. So both the reactions are redox reaction because both oxidation and reduction is taking place. See, you can balance these chemical equations, and for this equation, this is very famous chemical equation, and this is also known as Thermit reaction. So you can remember the name of this chemical equation, Thermit reaction, and it is also used to join the railway tracks, and cracked machine parts. So you can remember this chemical equation. So now we have learned how metals which are less reactive and metals which are highly reactive, they are extracted. Now let's see extracting of metals towards the top of the activity series, and we know the top elements or top metals, they are highly reactive. they cannot be obtained from their compounds by heating with carbon. See, they cannot be reduced directly by heating them with carbon, because carbon, they cannot reduce the oxides of sodium, magnesium, calcium and aluminium to their respective metals, because these elements, sodium, magnesium, calcium, aluminium, these have more affinity for oxygen than carbon. See, they show their reactions with oxygen rather than carbon. So that's why they cannot be reduced directly by using or by heating them with carbon or with reducing agents like carbon. And these metals, they are obtained by electrolytic reduction. So let's see how these reactions are taking place. So we have seen now that the highly reactive metals like sodium, magnesium, calcium, which comes on top in the reactivity series, they cannot be reduced by using reducing agents like carbon. So these metals are extracted by the process of electrolysis or electrolytic reduction. So these metals, sodium, magnesium and calcium, they can be extracted by electrolytic reduction of their chlorides. And aluminium, it can be extracted with the help of electrolytic reduction of its oxide. So these three, electrolytic reduction of their chlorides, and aluminium, electrolytic reduction of its oxide. So something like this we have. So here we have one cathode, two electrodes are there. So first one is cathode and second one is anode. So cathode, it is positively charged electrode. It is negatively charged electrode, and anode is positively charged electrodes. So electricity is passed. Since we are doing electrolytic reduction of chloride, so here we are taking NaCl. So aqueous solution means we will have ionic particles. Ionic particles means Na positive, Cl negative, like this. NaCl in its aqueous form, it will be broken down into its ions. So Na positive and Cl negative, and this thing we have already done while doing ionic compounds. Now let's see what happens here. So at cathode, which is negatively charged, this reaction will take place. Since it is negatively charged, so it will attract positive charge towards itself, so which is Na positive. So Na positive plus one electron, and we will get sodium metal. So sodium metal, it will get collected at cathode, because we are doing reaction at cathode. So the second reaction at anode, it is positively charged. So this reaction will take place, chlorine ion. So we will get chlorine gas at anode, because anode, it is positively charged and it will attract negative charge towards it. So chlorine plus 2 electrons, because the formula of chlorine we know, it's Cl2. So here also 2 ions of chlorine will get attracted towards anode, and for each 2 ions of chlorine, this reaction is taking place, and chlorine, it will get collected here at anode. Now let's do refining of metals. So we have already learned how metals of different categories, they are extracted. Now let's understand what refining is. So the metals which we have produced by various reduction processes, they are not very pure. So they contain impurities, and these impurities must be removed to obtain a pure metals. The most widely used method for refining impure metals is electrolytic refining, and now we are going to do electrolytic refining. So the setup of the electrolytic refining, it looks like this. Here you can see 2 electrodes are there, anode which is positively charged and cathode which is negatively charged, and both of these electrodes, they are connected to a battery, and here electrolyte is also there. You can see this setup is similar to electrolytic reduction. So let's understand this setup first. So here the impure metal is made the anode and a thin strip of pure metal is made the cathode. So anode, this is impure metal strip, and cathode, this is pure metal strip. For example, if we have to purify copper metal, so impure copper will be anode and pure copper will be cathode. A solution of the metal salt is used an electrolyte. So this is electrolyte. Since we have to purify copper, so copper salt solution we will take. We can take copper sulfate solution. Now when electricity is passed through this setup, can say here from anode pure metal, it will get dissolved into the electrolyte. On further passing the electricity, pure metal from electrolyte, it will get collected at the cathode. Now all the impurities are left behind, because we can see already pure metal from anode and from electrolyte, it is collected at cathode. So the impurities are of two kinds which are left behind. The first one is those impurities which are insoluble, and the second one which are soluble. So all the soluble impurities, they will get dissolved in this electrolyte, whereas all the insoluble impurities, they will get collected as anode mud. You can see here they will get settled down just below the anode, and they are also known as anode mud. So this was the process of electrolytic refining. This is how the impure metals, they are purified. Now let's do the related questions of this topic. Now let's do the related questions. So these questions are the textbook questions. So first one is define mineral, ore and gangue. So all the definitions we have already done at the starting of the video. Mineral, the elements or compounds which occur naturally on Earth's crust. You can, if you want, you can note down all the definitions, or at the starting of the video while I discuss this, if you want, you can take screenshot of all the definitions also. Second one is ore. At some places, minerals contain a very high percentage of a particular metal that it can be extracted profitably, and that is known as ore. The third one is gangue. The ores mined from the earth are usually contaminated with large amounts of impurities such as soil and sand. So these impurities are known as gangue. Now let's do the second question. The next question is name two metals which are found in nature in the free state. So we have already discussed the metals which are below hydrogen or the least reactive metals. All those metals, they can be found in their free state. So like examples we have taken gold, copper. So any metals or any two, because here it's mentioned name any two. So any two you can mention. So I will write gold and platinum. So sometimes they are available in the form of the sulfides also, and sometimes they are available in their free state also, gold, silver, copper. So any you can write, because it's mentioned any two, so gold and platinum. The next question is what chemical process is used for obtaining a metal from its oxide? So from its oxide it's mentioned. So two processes we have done. So first one, when we are using carbon as the reducing agent, so that you can mention as reduction process or reduction reaction. So this reaction you can mention. So we had zinc oxide which we have done after the process of roasting and calcination while doing the metals which are in the middle of the reactivity series. So first of all we have zinc oxide which we have got after roasting or calcination process, and this zinc oxide we are heating with the reducing agent carbon. Then this metal is reduced to, then this metal oxide is reduced to its metal and will get carbon monoxide. So this is the first method, or because chemical processes two are there. So first one is the reduction process, in which we are using reducing agent carbon. So oxide it's mentioned, so in here you can mention zinc oxide plus carbon, so we are getting zinc plus carbon monoxide. So full reaction you have to write along with the states, and you have to balance the chemical reaction also. Here I am not completing it, I have just written the chemical reaction, but you have to complete it. And the second one is displacement reaction, because if you remember in displacement reaction also, metal oxide, from metal oxide we are obtaining the pure metal. So we have done two reactions, first of the metal oxide of manganese and with the metal oxide of iron, which reaction is also known as Thermit reaction. So you can write any one reaction from those two reactions. So I will take this plus aluminium, so I will get iron plus aluminium oxide plus heat, because this is highly exothermic reaction. And you can mention the states also. Here I will mention the state. This is in solid state, this is in solid, this is in liquid state. Being a highly exothermic reaction, metal we are getting in molten state. This is again solid. Here also you can write the states. So along with the states you have to balance the chemical equations also. Now let's do the next question. So this is the question: in an electrolytic refining of metal M. So name of the metal is not given, it is represented as metal M. So what would you take as anode, cathode and electrolyte? See, refining, just now we have done in this video itself. In refining or in electrolytic refining, we take anode as impure metal. So you can write impure metal M, because name of the metal is not given, they have just mentioned any metal M. So anode it will be impure metal M, cathode it is pure strip of metal M, electrolyte it is salt solution of metal M. So we have already discussed these things while doing electrolytic refining, that anode it is impure metal, whichever metal we are taking. So impure metal strip it is anode, cathode it is pure strip of metal M, and electrolyte it is salt solution of metal M. So here name of the metal is not given, so that's why we are writing metal M. So this is all about extraction of metals. I am sure you have understood the concept. Thank you so much for watching the video. See you in my next one.